Hey, so today we're going to talk a little bit about machine learning weather prediction model development for global forecasts. This encompasses a lot of work that's gone on for almost, let's see, a year and a half, 2 years now.
Yeah.
And as we all know, in the machine learning world, 2 years is like a century of time in terms of since things develop so quickly. We're just going to go over a few things. So let's see here. All right, so we'll start with some overviews. This is just kind of a general outline of our talk. I'm only going to talk for the first 5 or 6 slides just to provide a general background and overview of how this fits into a broader NOAA endeavor called Project Eagle. And then Jun's going to really talk about all the really interesting scientific bits and pieces, how our deterministic system was put together with GraphCast, some additional training and fine-tuning that was done, and then some of the novel work that we've been doing in terms of developing a global ensemble system as well. So lots to cover there. So I'll just set the stage here with some bigger picture items. Some of this Eagle-based endeavor, and some of you may have seen or heard about Eagle and maybe some meetings or some discussions. There's actually a really wonderful blog post out now on the EPIC webpage. If you're curious to learn more, I'd suggest go to EPIC's page and head over to the blog there, and you can learn more. So a lot of this Eagle stuff, or the Eagle endeavor, was born out of some highlights from an AI for NWP workshop. And one of the broad outcomes from that workshop was that there's a big urgency to act. This field's moving very quickly. There's a lot of really awesome potential there, and the potential's already been demonstrated. And so we can do ensemble forecasts, but at a substantially reduced computational capacity. So you can potentially increase the membership or double the membership and augment your existing physical model-based ensemble with that. Improved skill. I think we've all been exposed to some of the really tremendous achievements in that category, and some new ways of doing operational NWP, new ways of doing business, and so on. And so there's just a lot of potential there that can be realized. And it was also recognized that we have a lot of efforts that are going on around our community in terms of checking out GraphCast and seeing what we can do with it, or ForecastNet or GenCast or any of these other applications that are out there. There's many of them. They're all very exciting, but we need a way in which we can all work together and combine our efforts so that we can advance what we're doing for NOAA, within NOAA, and then ultimately to improve our operational forecasts from there. So Eagle is a NOAA endeavor to develop and test forecast systems for deterministic and ensemble AI forecasts across scales, so from global to local scales. It will provide a near real-time testing and demonstration environment. So this is its very early stages right now. And we're looking to provide a structured environment to identify and incorporate AI innovation across the weather enterprise. So bringing these innovations into kind of one framework. All this will be underpinned by EPIC infrastructure and NOAA science. So it's a nice collaboration, a growing collaboration between OIR, NWS, EPIC, and the broader community. So like we said, it's a unified collaborative endeavor. So it's not just the work of a single lab or a single group. It really is more all-encompassing. So like I said on the prior slide, it's the Weather Service, NOAA Research, and well as EPIC, and that all combines together to form Project Eagle. So we've been talking about Eagle a lot, but I haven't actually said what it stands for yet. So it's a nifty little acronym that stands for Experimental AI Global and Limited Area Ensemble. So that kind of nicely wraps everything together. The experimental aspect of this is particularly nice because it allows us to innovate much more quickly. And so we can adopt more modern DevOps style development practices and get innovations into our prototype and experimental systems much more rapidly than we otherwise typically are able to do with a conventional NWP development paradigms. And we're looking to shift that as well to be more agile there, but Eagle's going to be a great pathfinder for that. So we have 2 systems going right now, and then a very nice data visualization capability. So there's Global Eagle Solo, and in this talk, in this presentation, you may see it referred to as GraphCast GFS as well. So that was in the earlier days before we had all kind of coalesced around calling the system Eagle. But Global Eagle Solo is the deterministic GraphCast-based system, that's trained on GDAS and initialized with GFS. The Global Eagle Ensemble is just an ensemble variant of GraphCast tuned on GDAS and then initialized with the Global Ensemble Forecast System initial conditions. So we're getting multiple sources of the spread from that system, and we'll go into June will be providing all the details of that in following slides. And then we have a really nice data visualization capability that was born out of a great collaboration with our friends and colleagues at the Global Systems Laboratory, or GSL, through their DESI framework. And so Eagle Solo and Ensemble are now being ingested into DESI in real time. So the runs are going on right now today, running on the cloud. And then those are now pulled over into this DESI framework, which is a really nice interactive data display system. So if you're not familiar with DESI, I encourage you to check it out. It's a really awesome framework. All right. And I think at this point, I will transition over to June.
Thanks, Jacob. Okay, now I will talk about the global deterministic and forecast system, Eagle Solo. So for this one, sometime we call Eagle Solo also GraphCast GFS. Some user was asking about this. This is actually Eagle Solo we're talking about here. And also sometimes we just call it GCGFS. If you need to know more details, I listed a NOAA office note published a couple months ago, so you can know more details on how the system was set up. A little bit of history for the Eagle Solo. So when 2023, the GraphCast model becomes available, we start looking into that. And the first thing we did is take the GraphCast and run with GFS analysis, which is GDAS. And we're able to set up a near real-time run. And I listed the current location of the near real-time forecasts. And we started looking at the forecast results. First, at that time, this is our first time to look into the machine learning model forecast. We would like to know what it performed compared to the current operational model. So one example on the right is a winter storm. So on the top are the two machine learning model forecasts, and the bottom left is GFS, and on the right, bottom right is our analysis. So you can see from the figure, machine learning forecast actually perform quite well. It is, at least for us, we have some thoughts on how the model will perform. Is that there maybe some physical inconsistency and those, but it turned out actually the model performs quite well. It catches the winter storm for the different fields. Say here you will see 500 millibar vorticity, geopotential height, mid-sea level pressure. They are consistent, at least in this case. So this gives us some confidence, and then we continue to move on to actually starting to train the GraphCast weather model using GDAS data because we start to notice some initial shock when we just directly use GDAS data with the GraphCast. As you all know, GraphCast actually trained with ZR5 as truth and input. So this is basic training details here. We're using for GFS, we only have, as 2024, we have 3 years of data. So we use 1 year for verification, 2023. And then for the training data, we're using 2021, March to 2020, end of 2022. And when we training the model, we actually fine-tune GraphCast from the weights provided by Google. So at that time, we were looking into say, okay, we have our GDAS data. Let's train from where the Google stop, and then we fine-tune with further the 2021 to 2024, which the GraphCast has not been trained for. And then we also here, we call it fully trained. As you know, some details about training, GraphCast actually trained for 12 autoregressive steps. So when we do fine tune, we start from autoregressive step 12. But when we do training, when we say training here, we actually training from the beginning. So beginning of the forecast and up to 12 step, which is 3 days. So here, a little bit architecture here. So we are using the data parallelization to train GraphCast. As you see, we are using a H100 node, and then we have 8 GPUs. So the model, the same model runs on 8 GPUs, but processed with different data. And the training loss showed on the right, as you see, the verification and validation and training loss, they are consistent. And then stabilized. So here are some results. In this figure, you will see 4 lines. Black line is operational GFS. Red is ECMWF. And then the blue line is what we call the fine tune, starting from the 3-day training weeks. And then the green line is what we call the training. We start from beginning, so AR step 1. As you see, this is the latest results, the last month. The 2 machine learning model actually performed quite well. During this period, it's even better than ECMWF. So this is a 500 millibar height anomaly correlation, and then wind vector at 250 millibar. Here are some vertical structure for potential height root mean square error. So for us, we know the model GraphCast is trained using the root mean square error, but we would like to see for the physical consistency on the vertical structure, how does it perform compared to the operational models. So in this figure, you see for Northern Hemisphere, Southern Hemisphere, and tropics. In each figure, top right is current operational GFS version 16. And the top left and top right is the difference of the trained model. And then the bottom is what we call the fully, is a fine-tuned one. If you see the green lines, basically those are green areas. Those are the areas that the machine learning model actually improved the vertical structure. So it gets a smaller root mean square error. As you see in the machine learning models, it does have improved area in the vertical pressure level, especially in the tropical region. But at the top, as you see, it has some degrading. Especially for the fine-tuned one, there are some degrading on Southern Hemisphere on the surface too. Now let's see the bias. So in this figure, the bias, this is just the bias. GFS is on the top left, and then you can see compared to operational numeric NWP model, both machine learning model actually has larger bias in all the Northern Hemisphere, Southern and tropics. And also the fine-tuned one has smaller bias at the Northern Hemisphere near the top, but the trained one has higher bias, especially on the longer lead time. But for the surface, you see it has smaller bias. So now let's see temperature. Similar story here. For the root mean square error, there is some improvement in the longer lead time in the middle level, but there are degrading in short lead time for both machine learning models. Bias, it's a similar story. We noticed that for the machine learning model, especially the trend one, it has negative bias in all the atmosphere levels. So let's look at precip. Many people really care about this this field. So in general, as you see on the left panel, it is day 1 precipitation average precip. and on the right is day 5 forecast. On the top row, it is observation, and then second one is operational GFS, and then we have the two. One is the fine-tuned one and the trend one. In general, as you see, the machine learning model actually gets the precipitation forecast pretty well. The shape and the also the value, it catches up almost the same as GFS. If you look carefully, you will see some smoothness at day 5 forecast compared to the operational GFS. Here we look into some more details on the total precip in different regions. We have maritime, continental, we have corners, we have a tropics region, East Asia, and also Indian Ocean and globe. As you see, the machine learning model actually catches the trend quite well. So this is regional average, and the vertical coordinate is the total precipitation, and then this is time. And in general, the two models perform quite similar to operational GFS, and it also follows the trend of the to the observations. So that does give us some confirmation on how the model performed for the critical meteorological field. Here is for the hurricane track. We look into the hurricane track performance. On the left, it is on the Northern Atlantic Ocean. On the right is West Pacific Ocean. This is for the track error, and the blue line is the current operational GFS. The red and the green, one is fine-tuned, and one is what we call the trend one. As you see on the Northern Atlantic Ocean, the track improvement is significant, up to almost 7 days. And even for the Pacific Ocean, it up to 5 days, we have improved hurricane track. But this is not true for the intensity. Here we show the intensity error. The blue lines is GFS, and the two lines for machine learning, you see the both models have much higher intensity error. This is known to many machine learning models. As we see, those models tend to have weaker hurricane intensity. And here we give a case for Hurricane Helene, happened in 2024, September. I just want to give you some ideas how it performs against our operational GFS. And on the right is the GDAS analysis data. As you see, the location compared to GFS is more closer to analysis. This is for day 3 forecast. Just give you some ideas about the performance. And here is a test case for Typhoon Gami. As you see, on the left is the GFS forecast, and on the right is the GraphCast forecast. This is a fine-tuned one. You can see in this figure, each color actually is one forecast. So basically the hurricane track forecast from one specific time. So and then the best track is in the black lines. As you see, from the beginning, I circled out several regions. You see the GFS in the beginning, it tend to go east, and then in the later days, it tend to go west. But for the machine learning model, it actually follows the best track quite well. Okay, now I will talk about some ongoing development for the Eagle Solo. We noticed the vertical structure. There are some, as we already see, in general, the machine learning model has a larger bias in the vertical structure for many of the meteorological fields. So one thing we noticed is that in the training loss function, the original graph cast, they're using the pressure weights. So this is the simple weights using pressure divided by total, all the certain level pressure sum. And when we are looking at this, we think maybe it might be better to use the density weighted, as we see. So this is density. So the loss function was updated. So we are using rho instead of directly pressure. So it is updated as this one. So hopefully we're thinking this will improve how the representation of the thermal structure of the model. So here we did some training, some basic results showing here. We look into the 500 millibar anomaly correlation compared to the current one we trained from GDAS1. As you see, the score is consistent, even though it's not, it is significant up to day 10. And then we also see the top level 250 millibar temperature. You see some improvement here. And then we look into the vertical structure. So this is GFS version 16. This is the trend version as we looked at before. So we basically want to use this as control. And on the top right is the one where we use this new density as pressure weights. So as you see, for the northern hemisphere, the improvement is significant. On the southern hemisphere, we see some degrading, but for the tropics, it also has big improvement compared to the previous. And here is the root mean square error. Same story. We see the improvement at the top. So basically, this is the difference from GFS version 16. So if it's red, then it's degrading. So you see the previous one and the current one. Unfortunately, for the southern hemisphere, we also see some degrading. But for the tropics and northern hemisphere, we see significant improvement there. Another work we are trying to do is to improve the hurricane intensity. And we see the paper from Chris from Canada Center. Their group is using a modified spherical harmonic loss function to improve the hurricane intensity. So basically trying to maintain the high scale, final scale features. So we followed their work and we start to train GraphCast with this EMC. As you mentioned, this is spectral adjusted mean square error. And then we look into the 3 runs. The first one is using the pre-trained DeepMind weights, but for all the 3 runs, we're using GFS as input. So the first one is using the GraphCast weights. And then the second one is the current, the trend weights, we call it test version. And this last one is one we trained using the Chris method. So as you see, this figure shows you, the blue lines shows you the power spectral ratio between the forecast and the truth. So if it's close to 1, that means it catches simulates the spectral well. And then the red line is the coherence. So as you see, the coherence doesn't change much, but for the if we directly use the Google DeepMind weight, and you see in the large scale wave, it does have improvement if we train the model compared to without training them. This long wave, like 1,000 kilometers around, they have some improvement. And after we trained the model with the EMC, you see the smaller scale ratio start to improve. So it's getting closer to 1 compared to the previous one. They actually the spectral, the amplitude start to decrease for those scales. So we're looking into more on this method to hopefully we can work with the Canada Center CRIS group and get the hurricane intensity improved. Now I will talk about the develop the Eagle ensemble. So we also have a tech note published. If you want to know more details, you can see the link here. So the idea here is we hope to develop a hybrid global ensemble system. To do that, we know that the machine learning model can run efficiently. A few minutes, you can run many ensemble members. But the idea is we want to have a comparable performance that can explain the ensemble uncertainty. So we developed the machine learning based global ensemble model. Basically, we fine-tune and train GraphCast using GFS data and several other data sources. So this way we use one machine learning model to run with our operational GFS 12 as the initial condition. And then we combined with current operational model, we can form a machine learning and NWP super ensemble. A little background on this is that how do we create those machine learning models that have good performance, and also we hope to get some good performance. So the idea is from Google DeepMind's paper. When they talk about GraphCast, they mentioned that when they train the model with different autoregressive steps, and different autoregressive step actually performance have slight different performance. For example, if you train the model with smaller autoregressive step, then it performs better in the short lead time. And when you train for the longer lead time, in their case, for example, 12, and those are performed better. So from this, we are thinking maybe when we training the GraphCast with autoregressive step, then we can use each of them as a ensemble member. So this way, a combination of model can give a better performance for all the lead times. So this is how we generate those members. For the fine-tuned one, we train the model with GDAS, with ER5, with high-res for 3 steps each. And then we also pick a checkpoint for those. So this way, we have 3 data sources and 3 steps. So we have 9 final weights, and then we get 1 more checkpoint. So total, we have 18 members. And then for the, we also train the GraphCast with GDAS as both input data and training and the truth. So we train them from AR step 1 to 12. So we got 12 members, and we also use 1 from DeepMind. So total we have 31 members. So after that, we did some analysis to see the different configurations. First, we just get control using DeepMind's GraphCast pre-trained weights, and then we run with GDAS have 31 member, and then the tuned one. So basically, we fine-tune the GraphCast. We got 1 weight weights, but we run the model with 31 member. We call it tuned, and then we have model. So basically, now we have 31 member, but we do not add perturbation from initial condition. So same initial condition drives 31 member, and then we also have mixed. So it has both model perturbation and initial condition perturbations. So we call it mixed, or sometimes we call it ML gaps or Eagle ensemble. And then the super ensemble, we just add the mixed plus the current operational NWP models. Here are some initial results here. Compared to gas version 12, as you see, this is a black line, and the control. So this is control is directly from DeepMind. As you see in the short V time, it performs the worst. Of course, on the other side, we compare to others. You can see this is the CRPS score. We use that for to evaluate the ensembles. For the longer lead time, we do see some improvement. But in general, the mixed, the light blue lines actually performed the best among those configurations. Of course, this is a single case. When we do the testing, we would like to get some ideas how different configuration performs. And then we run 1 month forecast using the mixed, or here we call ML gaps. And then we compare with operational gaps version 12, and we also use the super ensemble 62. So we have 62 members, and then we compare with operational. You can see in all those fields, the super ensemble actually performs the best, better than either NWP model or machine learning models. And then for the machine learning model, the red line, in some fields, for example, northern hemisphere geopotential height, it performs better, but for some fields, especially 2-meter temperature, it performs worse. But even for those cases, you see the super ensemble actually performs better than either of them. This is the root mean square error and spread, and we would like to check, especially on the spread, because we're developing the machine learning models. We hope it can give us different spread that comparable to the mean error. But in general, as you see from this figure, the machine learning model spread is relatively small, especially for some field like wind field. It's much smaller, opposite to the operational model, which has larger spread. But in general, if you look the super ensemble root mean square error and spread actually is quite well, performed quite well. This is ROC area score. This score, if it's closer to 1, it's the best. If it's closer to 0.5, we consider this is random. But anything above 0.5 means the ensemble actually can correctly predict events, then give a first log. So you see here the same story, the super ensemble actually performs the best, even though in some cases for the 2-meter wind, machine learning model is not perform as good as operational gaps. Here is for the hurricane. We look into the hurricane track for this single case. And as you see, the same story, the track is improved, but not the intensity. Both intensity error and bias. Machine learning model shows higher bias. Okay, here are some development work we have been doing for Eagle Ensemble. We start to testing and training GenCast. So GenCast model showed up in the end of 2024. And the model actually is a conditional diffusion model trained with 40 years of ER5. So we started looking into this, especially we noticed the blurry issues and the intensity issues. So we hope that we can use GenCast to improve, to resolve those issues. So what we do, we first start to run GenCast with GFS as the initial conditions. And we found some very large errors, the root mean square error, than the Eagle Ensemble. And then when we further looking to it, we noticed that GenCast is more sensitive to input data compared to GraphCast. So before we talk about the GraphCast solo, we did the same test using GFS and we verified the results. But when we do the same for GenCast, we found that GenCast, several cases we have been doing for winter, summer, and spring, and looks like GenCast does not perform as good as for example, the GraphCast if we are using GFS as input. So here is an example of 2-meter temperature. The blue line is GAPS version 12, and the red line is the mixed Eagle ensemble we just talked about. And then the green line is the GenCast GFS, we call it. So basically it's GenCast using GFS as input. And then we noticed that after a couple of days, the error grows significantly. So in this case, on the right, I give you an example how on day 9, so here, day 9, you see the large error. So the analysis on the top shows a big heat, the heat tone on the west of US. But if you see the GenCast forecast, none of them actually catch this event. So basically there's a heating going to the north during the forecast time, but none of those 31 members actually get that. And we also look into some winter case, we found the same issues there too. So we started thinking, yeah, we may need to fine tune the GenCast. We cannot directly use GenCast to do forecast. So we took GenCast and 1-degree model, and we also use the GDAS, the training data here, and GDAS input and ER5 as ground truth, since GenCast was trained with ER5. So this is initial testing. As you see, we do see the training loss and the validation loss for the period. Looks like they're stable, at least they're consistent. And then when we compare the forecast, as you see, so ER5 is on the left, and the forecast from the trend one, we call GC-GDAS, is the middle. And then on the right is GenCast, just use ER5 as input to drive the forecast. As you see, after 2 days, the GenCast with ER5 as input performs quite well. It is bottom right. But the we call GC-GDAS, when we using the trend model compared to ER5, it still shows very large big differences. So this is actually make us think of what happened for the even after training, looks like the model did not catch exactly, did not learn from initial condition how to correct this. So we did another test. So basically for the GDAS input, we replaced 2 fields. One is 2-meter temperature and the other is SST. So we just use the 2 fields from ER5, all the other fields from GDAS, which is the blue lines here. And you see, in this case, the original, this is a winter case. The original GraphCast GFS, the green line, it had very large root mean square error, if even out of the chart. But if we just replace these 2 fields, the error actually brings back. It is, at least you see, in the same group as other machine learning models. On the southern hemisphere, you see the green line from original. We kind of competed with GDAS data, and then the one with just 2 fields different. So from this, it tells us that 2-meter temperature and SST are very critical. Unfortunately, GDAS, we do have a little bit update for the SST field, since GDAS does not directly output SST in current operational model. So we were thinking we need to use either maybe UFS replay, or we need to use GFS version 17, which has consistent to meter temperature and SST field to train the model. Okay, a little bit future work. So we will continue our work on loss function update, finish the evaluation, and also for the two methods we're looking to, we will see if that can improve the model performance. Also, we will train the Eagle ensemble with the CRPS score. Kim just mentioned that NOAA has very good structure framework set up to do this, and we hope that can also improve the performance here too. We will train GenCast hopefully with GFS version 17 retrospective runs from cycled runs too. We will also collaborate with NOAA AI for NWP groups to develop the coupled Earth modeling system. Additionally, we have been working on to provide hurricane forecast products directly from the machine learning forecasts to the community. For us, collaboration is very important. At this time, when we do the training, we're using either the what are available for us, but we would like to transition to the NOAA as several groups have presented the results here. Evaluation method and tools are critical for us to understand the forecast, machine learning model forecast results. We hope we can have some collaboration there too. We will also collaborate with NOAA AI for WP groups, other operational centers, and private sectors to further improve Eagle forecast system. A few words on the challenges. First of all, data quality and consistency. As you know, when we present results, we see some inadequate considered training data actually can prevent you get the best results. Also, some knowledge gap. We're trying to understand why we got this forecast from the model. So we know that machine learning models evolve very fast, and we hope we use some tools at this time. Explainable AI tools looks like it is not that sophisticated yet for us to understand, but definitely that it helps us to know how to improve the model, give us some hints there. Again, collaboration on the new machine learning application development are critical too. So we hope knowledge sharing with operation centers and research community and private sectors can give us more opportunity in developing machine learning weather prediction models. Okay, I will stop here. Thank you.
So thanks, Jun. I think there's one hand, and there are a couple questions in the chat. So maybe whoever had their hand up can go first, and then I think we have time for a couple questions, if it's okay, Jun and Jacob. I just put two of them in the chat that were in there, and again, whoever had their hand raised, they can go ahead.
Oh, okay, thank you. That was a very interesting presentation. One thing that I'm interested on, I know a lot of operational centers post-process physical-based models by debiasing them. Have you guys thought about using machine learning, or some statistical technique to debias the AI models? So that's one question. And then the other quick question is, so GenCast is already an ensemble model, right? Whereas GraphCast, you have to run it with various members. You have to run it using various members of the physical forecast, right? And that's it.
Okay, first of all, for the bias correction, actually, in our group, Lin and Jun are have been working on a bias correction model, and maybe we can give you a tech note. We recently published on the bias correction. It is very effective to correct, for example, 2 meter temperature and other surface fields. So we are getting really promising results there. The second question, yeah, the graph compared to GenCast, GraphCast, we are running a GraphCast with operational initial conditions. Of course, when you run GenCast, you can add noise without actually using those operational initial conditions. That's true, yeah.
Okay, thanks, June. And there's a couple, I mean, maybe we have time for a couple more. I put 3 questions in chat. It was, I guess maybe the first one is, how do the Eagle models compare to AIFS is the first one.
First of all, I haven't directly compared with AIFS yet. So right now, our evaluation webpage setup is with ECMWS IFS. But definitely it's interesting to see.
Yeah, it's on our to-do list.
Yeah.
And
Yeah,
likewise, and likewise with the AIFS ensemble that's coming online here very soon.
Okay, and the second one is, are the intensity errors for the TCs related to the loss function, e.g. MSE-based loss encourages lower amplitude prediction?
Okay. Yeah, we actually hope that when we implement the spherical, the AMSE, it will improve both intensity error for all the wave numbers. That's the purpose. So basically, yeah, lower amplitude predictions. We hope that at least can catch the truth.
Okay, thanks. And just one last question in there, and then maybe one hand, but it says, when will the GFS V17 based initial conditions be available?
So the GFS V17, that's a great question on the V17 ICs. The GFS V17 team is working on kind of the later phases of the development there. So we're not quite ready to start sharing initial conditions, but we hope to in the coming months.
Okay, and there's a hand. Who I guess we do have time for one more. So over to you.
Yeah, I couldn't leave a message, so I'm just going to speak up. So, Jun, I have a question for you. So you mentioned the intensity error. So when you calculate the intensity error, do you use the intensity you get from ERA5 data, or you get from best track?
This is a question for my coworker, but my understanding is from best track.
Okay, so the intensity, but okay, so my point is the ERA5 data itself, the intensity actually severely underestimates the true intensity that we usually consider. I mean, not really true, just the intensity that we use for best track. So I think for when the intensity error, when the intensity is not really correct in the training data, you couldn't really expect to get intensity right using the AI model.
Okay, that's a really good point. Thanks for letting us know.
Okay, and I just double checked. So yeah, thank you very much, June and Jacob. Those were all the questions, and we're right at time. So really appreciate your presentation here. This was great. Thank you.
Thank you.
Thank you.